Hello, my name is Joshua, and I'm from Material Science, the January semester 2024. And today I'll be presenting a video presentation on strength, stiffness, toughness, and the correct properties, mechanical properties for material design. For strength, in the mechanics of materials, the strength of material is its ability to withstand an applied load without failure or plastic deformation. So the strength of materials considers the relationship between the external loads applied to a material and the resulting deformation or change in material dimensions. The strength of a material is its ability to withstand the applied load without failure or plastic deformation. So in designing structures and machines, it's important to consider these factors so that the material selected will have adequate strength to resist applied loads or forces and retain its original shape. However, we must note that the load which will deform a small component will be less than the load to deform a larger component of the same material. Therefore, the load is not a suitable term for strength. Instead, we can use the force per unit of area, called stress, which is constant until deformation occurs for a given material, regardless of the size of the component part. So in this concept, strain is also a very important variable since it defines the deformation of an object. In summary, the mechanical behavior of solids is usually defined by quantitative stress-strain relations. A deformation is called elastic deformation if the stress is a linear function of strain. In other words, stress and strain follow Hooke's law. Beyond the linear region, stress and strain show non-linear behavior, and this inelastic behavior is called plastic deformation. Stiffness is the material's ability to return to its original form after being subjected to a force. The stiffness of a material can be quantified by the slope of the stress-strain curve, and there are many types of stiffness, which, as you can see in the examples mentioned. And in general terms, the stiffness of a material is calculated by using the following equation, which is stiffness equals to force over displacement. The Young's modulus stress-strain curve, as you can see, is a good way of graphically demonstrating stiffness. The ratio of stress to strain is the elastic modulus, but the way a material responds to stress, and only the stress, defines the strength of the material. Toughness is the ability of a material to absorb energy and plastically deform without fracturing. So one definition of material toughness is the amount of energy per unit volume that a material can absorb before rupturing. It is also defined as a material's resistance to fracture when stressed. Temperature is one of the factors. Other than that is the notch effect, and also the static loads, the roughness, and which affects the toughness. So as you can see, there are three variables which can affect toughness. Toughness, and as you can see, this is the formula for toughness. Toughness requires a balance of strength and ductility. Toughness can be determined by integrating the stress-strain curve. It is the energy of mechanical deformation per unit volume prior to fracture. And to create a product design which is capable of resisting high deflection and absorbing high energy before failure, we need to take into account a product with high strength properties and high toughness capabilities. Strength is typically measured by the stress required to cause permanent deformation or failure, while toughness is measured by the energy needed to fracture material. Generally, generally stronger materials have higher yields and ultimate strengths, while tougher materials can absorb more energy before fracturing or cracking. So some examples of product design for these properties are saw blades and hammerheads lah. And so as a conclusion, the mechanical properties suitable for these criteria are materials with high toughness and high strength properties. Thank you.